to this talk on using Google Cloud Functions to build a serverless Slack bot for fun and no profit. My name is Prasidha Bista, Pras for short, and I'm a software engineer at Stacks. You can scan the QR code on the slide to follow along with the slides today. I wanted to start off by asking a quick question to everyone here today. How many of us in the group are familiar with 2 or more cloud providers? For instance, Amazon and Google, Google and Azure, and others. A few. I asked this question because my day-to-day job involves working with Amazon Web Services, but I've been able to build this application in Google Cloud, so I'd really appreciate any feedback that you might have for me after this presentation. Stacks is an AWS cloud management platform, which enables organizations to quickly build and renovate on the cloud, whilst taking care of necessities like security, identity and access management, cost and compliance, risk management, and reporting. Stacks has also built a total cost of ownership calculator, which anyone can play around with by visiting stacks.io/tco-calculator, which will give you a quick representation in terms of the cost difference in having to build a solution like Stacks versus buying it outright. Back in 2018, at Google Cloud Next conference, Urs Husley, who's the SVP of engineering at Google, said that building a successful application requires more than just writing software. It entails implementing best practices around security, cost management, compliance, and risk mitigation. A well-rounded approach is key to delivering a reliable and scalable solution. So have you answered questions like, is your application secure? Is it compliant against certain rules and regulations? Have you thought about, is your application cost optimized for cost? And have you thought about all the risks and how to mitigate those risks as well? So if you keep this quote in mind, we'll see how this quote relates to this presentation on the serverless Slack bot as well. The agenda for today, we'll talk about the serverless Slack bot. We'll see how we can test it locally, how we can deploy it to Google Cloud using Terraform. We'll see how we can implement continuous integration and continuous delivery using Github actions and short-lived OIDC tokens. We'll then dive into a quick demo on how the Slack bot works. We'll then see how we can use Google Cloud provided tools to monitor the health of our application in terms of logging, monitoring, and tracing, which will then be followed by a few slides on key takeaways. And we'll finally end with a quick note on Explorer Slack community, which is where the Slack bot runs. The architecture itself is really simple. We subscribe to a few events in Slack, and whenever those events occur, Slack will then forward those events to the Google Cloud function. The function will then process the Slack event and respond to Slack accordingly. For instance, if a new user has joined the Slack workspace, the bot is going to then welcome the new Slack user. And if a user has posted a message in the Slack channel, the bot will then scan the text for any keyword matches for emojis. And if it finds any, it will react to that Slack post with 1 or more emojis. And we'll look into this practically in the demo section. In terms of the technologies used, Slack for event subscriptions, Google Cloud Platform to deploy the application, Terraform as the infrastructure as code tool to deploy the application to Google Cloud, TypeScript as the programming language of choice, Github actions for the CI/CD pipeline, and finally Sonar Cloud as a code quality and security analysis tool. You can also visit these URLs at the bottom to look at the application and CI/CD code. So what is Google Cloud Functions? Google Cloud Functions is a serverless pay-as-you-go compute environment which lets you build applications without having to worry about managing servers. It is stateless, it's ephemeral, and it scales automatically on Google Cloud's infrastructure. There are 2 types of Google Cloud functions: HTTP functions, which you invoke using a HTTP or a HTTPS URL, or an event-driven function, which gets invoked or it gets triggered when an event is emitted in the cloud. For example, if an object in a cloud storage bucket is deleted, that can be an event that triggers your cloud function. There are many use cases for cloud functions. It can be used to build web applications as backend as a service. It can be used to process large amounts of data as a batch processing service. It can be used to build APIs and automation. And it's heavily used in event-driven workflows. There's also 2 generations of Google Cloud Functions, Generation 1 and Generation 2, and we'll talk about it in a bit. There are 2 components of Google Cloud Functions that are open source, namely Cloud Native Build Packs and Functions Framework. Cloud Native Build Packs gives you ability to run a Docker container locally, which you can then invoke to test your application, which it basically mimics your Cloud Function environment, which you then invoke to test your application. And the other one being Cloud Functions Framework, which we're using in this scenario, which lets you run a HTTP server locally, which you then invoke to test your application. Now that we've seen how we can test the application locally, which helps you get started really quickly, but then once you want to be able to test integration and other things, you then want to deploy your application to Google Cloud. And the way that's being done here for this application is by using Terraform. And the way this works is Terraform first authenticates to Google Cloud using your application default login credentials. Then when you run Terraform init, it initializes its backend, which is cloud storage in this scenario. This is also where Terraform stores its state file. And state file is where Terraform stores all the configuration changes that it's making to your cloud provider. This is also when Terraform initializes all your providers and plugins that you might have in your Terraform project. Then when you run Terraform plan, that gives you a quick representation of the changes Terraform is planning to apply to your cloud infrastructure. It hasn't really applied it, it gives you a quick plan that you can see and assess before you apply those changes. Then when you're happy with the plan, you run Terraform apply, which actually goes ahead and applies those configuration changes to your cloud infrastructure. Then finally, when you're done testing and you're happy with the tests and everything, and if you want to delete all the resources that Terraform created, it's again a simple command, Terraform destroy, which destroys all the resources that it had created earlier in your cloud infrastructure. Then finally, when you run Terraform apply, that's when it deploys the cloud function. When you deploy a cloud function, let me take a step back. This is a quick example of having run Terraform apply, where you can see that it took about 1.5 minutes to deploy the cloud function and its resources. And it's added 2 resources, changed 0, and destroyed 1 as part of the update. When you deploy a cloud function, there's actually a few steps that happen behind the scenes. What happens is it actually triggers a build process in Cloud Build Service. That build process then fetches the application artifact from cloud storage. That's a zipped up version of your application. It fetches that. It creates a Docker image out of the application artifact. Once it creates that Docker image, it then publishes that Docker image to either a container registry or artifact registry. Then finally, when you deploy Cloud Function, that then points to that image in either of those registries. So because there's these few steps go on behind the scenes, it is important to note that there might be additional costs for having used these services as well. In terms of managing secrets, Google provides a service called Secret Manager, and we're using Secret Manager to store the Slack token. That token is then available to the function, to the application, as a mounted volume during runtime, which you can see on the bottom right corner of the slide. It gives you a secure way to pass secrets to your application. In terms of identity and access management, both GitHub Actions and Cloud Functions have a service account associated with them. A service account is a special type of account in a Google Cloud project, which has a unique email address, and is generally associated with a service or a resource rather than a user. These service accounts are then granted custom IAM roles with least privileged permissions to interact with Google Cloud services. For instance, in this scenario, GitHub Actions can only do things like deploy the Google Cloud function, deploy IAM permissions for the function, and be able to interact with cloud storage to fetch or upload the application artifact. On the other hand, Cloud Functions can only perform actions like fetch the application secret from Secret Manager and be able to interact with cloud storage to fetch the application artifact. So we basically only allow these services permissions that they need to interact in order to perform their jobs and nothing more. We can also use common expression language to further restrict permissions to specific resources only. For instance, in this scenario, we've created a condition expression that targets a specific artifact bucket resource, such that when GitHub Actions assumes this role, it can only interact with this one particular bucket using these restricted permissions. So we effectively implemented permissions with least privileged access in mind. And if you think about it, there could be a lot of buckets in your project which you don't want all these other services to interact with. And this is one way for you to restrict those permissions to be able to interact with certain resources only. Because if you only look at the permissions on top, those permissions, if you don't have the condition at the bottom, those permissions apply to all the buckets in your project, but as soon as you have that condition restricting that access to a specific resource, this role can only perform actions against that specific resource, which is the artifact bucket in this scenario. Now that we've seen how we can test the application locally, how we can deploy it to Google Cloud using Terraform, once you deploy the application, you get a HTTP or HTTPS URL to invoke your function. That's when you navigate to Slack. You create a Slack app. Then when you navigate to event subscriptions, this is where you enter the endpoint or the HTTPS URL of your function. This is also where you tell Slack what events you want Slack to forward to your function. And in this instance, Slack will forward events when a new user joins the Slack workspace or when a user has posted a message in the Slack channel that the bot is invited to. The other thing that we need from Slack is the bot token. Because if you think about it, how does the application interact with Slack? How does it react to a Slack post? How does it welcome a new Slack user? It needs some sort of authentication, and that is done using this bot token. This is also where you define what scopes the token has, which means basically what is this token allowed to do in your Slack workspace. And in this instance, it can only do things like react to a Slack post, read emojis from a Slack post, and to be able to welcome a new Slack user when the user joins the Slack workspace. So only these permissions. And that is all you need in terms of setting up Slack. Let's look at CI/CD. How do we implement continuous integration and continuous delivery with a solution as such? Traditionally, creating a CI/CD pipeline between GitHub Actions and Google Cloud involved creating a service account in your project. You'd then need to create a private key for that service account. Then finally, you'd store that private key in GitHub as a secret. Now, if you think about it, this creates a secrets management problem, because every time you create a secret in Google Cloud, you need to duplicate it to GitHub Actions, GitHub as a secret. This also creates a risk of those secrets being leaked because you're moving secrets around. And finally, if you have organization level policies applied, for instance, disable service account key creation, I think it's called, you're then effectively no longer allowed to create private key for your service accounts, which basically effectively hinders developers' productivity. Now, let's look at how we can implement the same CI/CD pipeline using short-lived OIDC tokens. We first create cloud roles in the cloud provider, which trusts GitHub's OIDC provider, right? Once you create that role that trusts GitHub's OIDC provider, whenever a GitHub action workflow runs, GitHub's OIDC provider auto-generates an OIDC token, which the workflow then presents to the cloud provider. That token has claims and all the data that the cloud provider needs to authenticate that specific token. Once the cloud provider is happy with the authentication, the cloud provider sends back a federated cloud access token, which is a short-lived token for that workflow to interact with Google Cloud Services. So that workflow will then use that token to interact with the Google Cloud Services for the duration of that workflow. So it's effectively a short-lived token that gets used for a few minutes for the duration of that workflow, and then the workflow can no longer use that token anymore. So it's basically a short-lived token for a short-lived action. And as you can see, this provides a way of seamless authentication between the cloud provider and GitHub Actions. Because of this, we no longer have to store long-lived secrets in GitHub. And because we're allowed to implement custom IAM roles, we can also implement permissions with least privilege access in mind, because we are allowed to define what permissions these services are allowed to interact with Google Cloud Services. Now, in terms of the GitHub Actions workflow for this application, the way this works is Terraform first authenticates to Google Cloud, but this time using Workload Identity Federation. Previously, it used your local application default credentials when you're deploying it locally, but in the CI/CD environment, it uses Workload Identity Federation. Workload Identity Federation is an identity service in Google Cloud, which lets you manage external identities. In this instance, it's GitHub Actions, which is an external identity for Google Cloud. Once it authenticates to Google Cloud, it then uploads the application artifact to cloud storage. Obviously, it interacts with the state file at the same time, and then it finally deploys the cloud function. We'll look at this in a bit in the demo section as well, but as we know, it deploys the cloud function, but it triggers a whole lot of build process behind the scenes, which we looked at earlier as well. We'll look into a quick demo on how the Slack bot works now. This is a test Slack workspace that I've got that I'll be using to showcase the demo. What I'll do is I'll go in here and I'll invite a new Slack user. Basically, this is my own email with a test suffix. What I'll do is I'll go ahead and I'll accept the invite, pretending to be a new Slack user. As soon as I do that, I just join, and as you can see, the bot has welcomed me as a new Slack user. Hopefully everyone can see this from the back. The other bit that I wanted to show you was when I type in something like a post where I say, let's talk about Kubernetes, for example. Hopefully the bot then reacts with Kubernetes emoji, which it did. And as users, we also like to edit our posts. What happens if I edit the post and add another keyword, like JavaScript? Hopefully the bot then picks it up and reacts with a JavaScript emoji, which it did. The other bits that I wanted to show you before we move back to the slides was as you make changes in your feature branch and as you push those changes to Google Cloud, it automatically runs your CI tests. And in this case, I've configured it to run unit tests using Jest, which you'll see here. So it's basically using Jest, and it also gives you a quick test coverage as part of the CI test. Obviously, you can do a lot more as part of your CI test. This is just an example where I've run a simple unit test, but it can do a lot more. Also, when you develop your feature in your feature branch and you want to merge it to your mainland branch, whether it be master or main, once you merge it, it then deploys the application to Google Cloud automatically. And as you can see in this scenario, it first sets up Terraform, authenticates to Google Cloud, that's using Workload Identity Federation, sets up the SDK, and then finally, if we look down here, initializes Terraform, and hopefully down here, it deploys the application to Google Cloud automatically. So this is not me or anyone else going in and randomly manually typing in a command to do it. This is automatically when I've merged this change to my mainland branch, it's automatically kicked it off and it's deployed the application to Google Cloud without me having to do anything. I'll just move back to the slides. I hope you liked the demo. Wasn't a lot of it, but yeah. Now that we've seen how we can test the application locally, how we can deploy it to Google Cloud using Terraform, how we can implement CI/CD pipeline, and also a demo, we now need to think about things like how do we monitor the health of our application? How do we know if it's available, if it's performant, if it's performing to the expectation, is meeting all the expectations that we need it to meet? How do we know that? For that, we can use Google Cloud's provided logging, monitoring, and tracing tools. In terms of logging, Logs Explorer can be used to view the logs for your function. You navigate to Logs Explorer, and you construct a query where the resource type is Cloud Function, and that shows all the logs for your Cloud Function. Similar to Logs Explorer, these logs can also be viewed from the Cloud Functions console. So either way, you can go to your Cloud Functions console, or you can navigate to Logs Explorer and view these logs. In terms of metrics, if you want to know things like memory usage, instance count, execution times for your function, you can navigate to Metrics Explorer, and this is where it's going to show you all the metrics for your function. Similar to logs, these metrics can also be viewed from the Cloud Functions console. In terms of tracing, cloud tracing is being used to trace the application. It gives you a quick representation of how long things took within the application. This is really useful when you want to debug, for example, slowness in the applications. How do you know when things are taking a little longer, or when your application is a little bit slower? How do you debug that? I think cloud tracing is a perfect tool for you to be able to trace that, because it can show you exactly where your application took how long. For example, making an external API call, maybe it's doing a lot more retries there, maybe it's taking a long time. Cloud tracing you can use this tool to then quickly see what statement in your application is actually causing that. It might be an API call. So this is where you find cloud trace as useful in order to trace and find out how long things are taking within the application. Google also has an error reporting service through which all the errors happening in your project flow through it. In this instance, and this is also where you subscribe to notifications. And in this instance, what I've done is I've subscribed to Slack notifications such that when I raise a random error from my application saying, hey Slack, this is an error just for you, Error reporting then forwarded that error to the Slack workspace, the channel that I told it to. What this effectively does is it allows you to look at errors from your SIEM system. It doesn't have to be Slack. It could be Splunk, it could be Datadog, it could be anything else. But if you like Slack like me, if you're always in Slack like me, I prefer logs to be piped into Slack because that's where I'm always active. So if you're like me, if you like seeing logs, errors, everything flow into Slack, this is one way to enable that notification. And obviously it supports a lot more than just Slack as a notification target. Let's talk about a few key takeaways. Getting started with serverless functions in Google Cloud is really easy. In this example, we saw how we can use Terraform to deploy the application to Google Cloud. But you don't really have to. You can simply log into the Google Cloud console and in your favorite programming language of choice, whether it be Python or Node, create a cloud function right from there. But if you remember the quote from third or fourth slide where Urs Husler, who's the SVP of engineering, spoke about thinking about best practices around having to build a solution like such. For example, IAM, security, identity and access management, cost and compliance, logging, monitoring, tracing, and others. It's really important to start thinking about all of these things if you want to productionize your app. So it's easy to get started, but if you really want to productionize your app, or if you want a lot more users to start using your app, you need to start thinking about all these other things that you require to be able to make it ready for others to consume. You can't just let it be a public endpoint where anyone can do whatever, right? You have to think about security, you have to think about cost, how many times is your function being invoked, by whom, from where, all of those other things, right? The other takeaway is that Cloud Functions Generation 2 is basically Cloud Run service under the hood with all its performance. So Generation 2, even though you deploy a Cloud Function, you're basically deploying a Cloud Run service. So if you go navigate to Cloud Run, you'll see that that's where it's actually running your code as a container. So that was a bit of a surprise for me when I was learning Generation 1 and Generation 2 and the differences between them. Cloud Run is basically a managed container service offering from Google Cloud, which obviously scales automatically. It's got all the serverless characteristics, like Cloud Function. And in terms of performance, Generation 1 can handle up to 1 request per function instance at a time, but Generation 2 can handle up to 1,000 requests per function instance at a time. So a single instance of that function or the container can handle up to 1,000 requests versus just one for Generation 1. Generation 2 also supports a lot more events than Generation 1, and it also supports increased timeouts. So for you to be able to run long-running operations inside your function. And this is what I really like about Generation 2, the feature called traffic splitting. So for you to be able to deploy 2 versions of the same application and to be able to split a percentage of traffic between them. And if you think about it, this is really useful when you want to do something like an A/B testing, where you want to test your new feature with a subset of users before you release it out to everyone else in production. And this gives you a perfect way to do that by splitting, let's say, 5% of traffic to the new feature, and 95% of your traffic still goes to the older version that's running for everyone else. And that gives you confidence in being able to test a new feature before you release it out to everyone else. Now, if you decide to use Generation 2, there's a few things that it's good to remember. For instance, if you remember in the previous log slide, in order to view the logs for your function, you'd construct a query where the resource type is Cloud Function. But this is a little bit anti-pattern where if you want to find the logs for your Generation 2 function, you have to construct a query where the resource type is Cloud Run Revision, because as we know, it uses Cloud Run service under the hood. Also, in terms of permissions also need to be applied to different services. For instance, Cloud Build to be able to interact with the container registry or artifact registry to store the image, and also Cloud Run for users to be able to invoke the function. Previously, you'd apply these permissions to Cloud Functions, but now because these services are being used under the hood for Generation 2, you now need to customly apply these permissions to these other services as well. So it would be good to remember these things if you start with Generation 2. The other takeaway is that Slack expects a response within 3 seconds of the request. There's a concept of cold start within Cloud Functions, where Cloud Functions takes a few seconds, up to like a few seconds to initialize the execution environment before you can actually receive the request and respond to Slack. So there's a bit of a gap between when the Cloud Function initializes the environment, warms it up, before you can actually process the event. So in scenarios where the function takes longer than 3 seconds, what does Slack do? Slack's like, sends a request, 1, 2, 3 seconds, doesn't get a response back. Slack's like, all right, that request failed, I'll retry the request. So Slack will then retry the same request and invoke our endpoint with the same payload more than once, right? Which is not ideal. We don't want our function to process the same event more than once. For example, if a new user has joined the Slack workspace, it would not be ideal if the bot welcomes the Slack user twice, right? So how do we get around that? One way to get around that would be to create an API gateway in front of the function. So you're not just invoking the function directly, but you're invoking an API which is in front of the function. And what that allows you to do is the API gateway can then automatically reply to Slack with the 200 OK immediately as soon as it gets the request. So it doesn't wait or anything, but then it asynchronously invokes the function behind the scenes. So the function can take a little bit longer to process the event, but as far as Slack is concerned, it's happy because it's received a response with the 200 OK. Because the API gateway is like, oh, here you go, Slack, this is your response, we're all good. And the function then handles processing of the event. And if there are any errors, anything, we might have dead letter queues, notifications, and alerts and others set up for the function. So this is one way to handle a scenario where you don't meet contracts between two systems, right? One system expects a response within a few seconds, the other one cannot process it within that time frame, takes a bit longer. How do you deal with that? So this is sort of one way to deal with that. Final point, you might ask, why build a Slack bot? Why build a Slack bot in the first place, right? The main reasons for building a Slack bot is because it drives engagement in the Slack community. When we are able to do simple things like that, it sort of makes it fun for everyone to use the Slack workspace. I've been able to learn programming languages by doing this. So first wrote this application in Python, then I've written this same application in Golang, and now in TypeScript. So I've been able to learn a lot of programming languages by building the same bot. But for me, it's about learning while I do this. I've also been able to learn cloud technologies by building this application. So I work with Amazon Web Services on my day-to-day. But because I built this application in Google Cloud, I've not just been able to learn Google Cloud, but as of last 2 weeks ago, I'm also GCP Associate Cloud Engineer certified. So it was an amazing milestone for me to have as part of learning to build on Google Cloud. And finally, currently it only does a few things, right? It welcomes a new Slack user, reacts to a Slack post. But as you can imagine, the possibilities are endless. It can be made to do a lot more. For instance, it can make us productive by creating Zoom meetings. It can run quizzes in the Slack workspace for us to be able to learn together. We can also integrate ChatGPT right here into Slack so that users don't have to leave Slack to interact with an AI. And the possibilities are basically endless for a serverless solution like this. With that, I would like to talk about Explorers. This is where the Slack bot also runs. Explorers is a community of tech enthusiasts, like everyone here, where everyone comes together to learn and share and grow with each other. Whether it be personal development or career development, we're always there to bring the best out of each other. And we also like to help others or graduates and other people who are trying to find a job in the IT industry, especially when they're starting out really early, by reviewing resumes, conducting mock interviews, but mostly by being able to listen to them and being able to see what they're doing right versus doing wrong, and by being able to guide them to do the right thing. And as humans, we get the greatest joy and satisfaction by being able to help a fellow human being. And when we're able to spend a little bit of our time, not money, not anything else, a little bit of our time, and just sharing our experience and our knowledge. And if that helps someone get a job, change the way they talk, anything that, if it helps even like 5% in their life, I think that fills my heart with joy and satisfaction. It makes me really, really happy to be able to make a difference in other people's lives. So with that, I'd really like to thank all my friends from Explore Slack community who've come here to support me today. I'd also really like to thank all the organizers, Keshan, Matt, Gary, and others who've given me this opportunity to come and present in front of you all today. And with that, I'm open to questions. You can also add me on LinkedIn by scanning the QR code on the slide today. And I hope you liked the presentation. Thank you. Was it too hard? Was it too boring?
to make all the whole Slack bot into a Twitter bot?
Into
A Twitter bot.
Twitter bot.
Yeah.
A Twitter bot.
Yeah, yeah. What are the changes that has to be done? Because I guess it's also open source now. So
Yeah, if I think about it, you probably wouldn't have to change anything. You probably wouldn't have to change anything on the Google side. You still have a function that processes the Twitter event, for example. You basically probably just subscribe to Twitter events. Right? I don't know if you can just subscribe to events in Twitter. Basically, you need a way to forward those events to your cloud function, but then everything else is the same, right? You just have your logic inside your function that takes care of what you need to do inside Twitter. For example, if you want to modify the event before you show it to anywhere else. But I don't think there's going to be a lot of changes on the Google side of things. You still have a function, you still have all your logs, you still have all your monitoring, tracing tools that you use in order to monitor your application. CI/CD would kind of be the same because you still want to be able to deploy as soon as you merge to your mainline branch. So I think, yeah, there won't be a lot of difference at all. Same model, right? You're subscribing to events, you expect those events to be forwarded to your function, then you do some sort of thing with those events and respond back to Twitter or wherever the user is. Yeah, I think we can even pair on this if you want. You can add some AI capabilities to the bot, and I'll just write all the code like everything else. Yeah, pretty cool. Thanks for asking.